Welcome and hello. This is a video exercise in RIMS, and in this video, we're going to be dealing with reservoir system storage balance. What that means is when we have multiple reservoirs that make up a system of reservoirs, how do we want to balance the storage or the volume of water in those reservoirs with respect to the other reservoirs in the system? So we're going to go ahead and do a quick example in this lesson of how to control that using RIMS. What you see on the screen here is a very simple model schematic of what we're going to be dealing with. We've got three reservoirs represented by these blue triangles. This is our system. We have inflows for each of the reservoirs and then releases from the reservoirs through these channels C14, C24, and C34 that lead down to this node 4 and ultimately out of the system. There's also going to be a requirement to set a minimum flow rate downstream of the system. And then the other objective is to fill up the reservoirs as much as possible. So we're going to dig into all of those details. This is an exercise, so I plan to do every click and hopefully show everything so you can follow along if you wish. Alrighty, here is my project directory. There's currently nothing in there, so we're going to go ahead and start from the very beginning. In RIMS, I'm going to go up to File, New, Project, and then with General Project selected, click on Next. Type in or paste in the name of your project, and then for this checkbox, I'm going to uncheck it. Come over here to my project directory, highlight the path to that directory, and then paste it right here for the location, and then click on Finish. Okay, so that added a .project file in my directory. Next, what I want to do is define a launch file configuration associated with this project. So I'm going to go right-click on my project over here in the Project Explorer panel, come down to Run As, Run Configurations, right? And come down here to WRESL/RIMS2 application, click on New. This gave me a new configuration. I'm going to name that configuration E5 for exercise 5, Reservoir System Storage Balance. And then I need to provide some values here. So for instance, the main Russell file, I'm going to put in a run directory. We call it main.wresl. All right. For the DSS files, I'm going to put them in a DSS directory, which I haven't created yet, but we will in just a moment. dv.dss, dss/state variables will be an sv.dss, and then the init file for our initial conditions. That'll store the initial conditions of the volume of the reservoirs. That will also be in a DSS file called init.dss. Okay, these are relative paths. No groundwater folder. Let's go with a part A. I'll just call it project. Our part F in state variable, and then part F for init variable will be init. I'm going to go with the 1 month time step for the simulation. And then let's go for, how about a 6-year time window? So 1921 to 1927. And then that looks good right there. The next tab over is configuration. Go ahead and click that, and then make sure to check on this Russell Plus interpreter. And then the far right tab, which you may or may not see if you don't just click the chevron here, it's common. Go ahead and click on common, and then click on shared file, click on browse, and then select the project that we created. All right, then click OK and apply. After you click apply, you can close that configuration, and it should have saved a launch file right here in your project directory. All right, next I'm going to set up my directory structure for the project. And this is what it's going to be right here. I have the main project directory, and I already have these two files at the bottom, the launch file. Well, it's called something else. There we go. E5 Reservoir System Storage Balance.launch. That's the name of the launch file. And then the project file. And then everything else here is just a bunch of directories and files that I'm going to set up manually. If you've done projects like this before, you may have a template already set up where you can just copy paste some of that in. But if you're doing this for the first time, I'm going to show you how that's done. All right, so here is my project directory once again. Let's start by going a right-click, New, Folder, and this will be my DSS directory. Oops, that's lots. There we go. I'm going to drill into my DSS directory and create the three files, New, and then I'll just start with a text document and then rename the extension. So this will be dv.dss, delete the .txt on the end, enter, enter. And then I'm going to just make a copy of that. This will SV for state variables, and then one more time for init. All right, so that's set up. Let's go back up to the main project directory. After that, I've got a bunch of stuff inside a run directory. So right-click, New, Folder, and Run. Let's go into that directory. The first file is going to be a main.russell file. This is what we're going to reference first when we launch the file, because what's going to happen is you go to your run configuration right here, select on the configuration, and then this run/main.russell file is the name of the file that we're going to create, and it's going to basically orchestrate the entire script. Right click, new, and then boom, there's the Russell file. Okay. And then we need a directory for lookup. So right click, new folder, lookup, and one more directory for system, new folder, system. Okay. Inside the lookup directory, I'm going to create a file for the inflow data and the demand data. So here is the new file. It's going to be inflowdata.table, and then same thing for the demand data. So I'm just going to call that demand data.table. Oops, just like that. All right. And then inside the system directory, I'm going to go up a level to run, and then system, same thing. We just need to create a few different Russell files. So right click, new text directory, channels.wresl. Okay, there's the channels file. All right, so off camera, I added the other files. They're all blank, 0 kilobytes. All right, so the first thing I want to do is define the initial reservoir storage. If I go up to project and then DSS, that's going to be contained in this init.dss file. So let's fire up DSS view. I'm going to go file and then open, and then navigate to the project, and then the DSS directory, and then init.dss. Okay, there's currently no paths. That's good. We just created the file. Data, manual time series data. I'm going to come down here to the path name and then just paste in the different parts. So this is project. This is going to be for Reservoir 1, storage, 1 month, and init for part F. All right, I'm only going to initialize the first few months because we don't need to look back 12 months or 20 months or anything like that. I'm going to say July of 1921. The time will be at 2400 hours. The units will be in 1,000 acre feet, and then the type will be period average. All right, so I'm going to start this off with 80,000 acre feet. So I'm just going to type 80, 80, and 80. That's good because our simulation is going to start right here in October 1921. That's the beginning of water year 1922. Okay, so save that. And then here is the path. I'm going to make a copy of this path and basically start all 3 of my reservoirs at the same initial volume of 80,000 acre feet. So right click, duplicate. The only thing I need to change here is this part B. I'm just going to change it to reservoir 2, and that looks good. And one more time, right click, duplicate, and then reservoir 3, and then OK. All right. So we have our initial data right here, the starting storage in our 3 reservoirs. Next, we need to populate all the data in those .table files and those .russell files. So let's go ahead and start opening up the files and adding some code and some data. So run lookup. Here is the demands data table. I'm going to bring that to the screen here. Also, I'm going to open up the other table while I'm at it, inflow data table. So here are my tabs representing different files across the top. Let's go ahead and just open up all the Russell files as well. So I'm going to go up to run and then system, and then all of these files and open. And then there's also the main file, which is just inside run, and boom. Okay, bunch of files to edit. Let's go ahead and get started. To save time, I'm just going to paste in the data and explain what I think is most important. So I pasted in the data here for the demand. What we have is the name of the table, or a couple comments at the first 2 lines, the name of the table, which matches the file name, .table, and then month, and then this is going to be the demand through that downstream most channel, which is leaving the system. So this is downstream of node 4, which is this channel right here. Here are the different demands. This is the minimum in-stream flow. We have 100 CFS. It ramps up to 220 CFS and then back down to 100 over the course of a 12-month year, and that repeats year after year. All right, the next file over is the inflow data. I'm just going to paste in again. The first couple lines are comments. Inflow data is the name of the table and hence the name of the file. Then we have in the first column the month 1 through 12, and then the next 3 columns over is the inflow in CFS for reservoirs 1, 2, and 3. So you can see how over the course of 12 months, the reservoir inflow changes. I purposely made it semi-random and also peaking at different times just so we could really test out the RIMS engine to make sure that it's working based on some fairly random looking data. All right, the next file over here is inflows. Here is our inflow data. What we're doing is for each reservoir, we're identifying the inflow with a variable. Inflow underscore res1, for instance, is grabbing the data in the res1 column of that inflow table right here, 52, 58, 64. That's from the inflow data table where month equals month. Same thing for all three reservoirs. The next table over here is similar. It's demands. What we're doing is defining the demand as a state variable. We're reading from the C underscore 4 underscore capital O field from the demand data table and file, which is right here. So those are the in-stream flow demands. The next file over is the channels. So here is what I have there. We have 6 decision variables. So we have a decision variable for the flow through channel 1.4, 2.4, 3.4, and then channel C40 actually has 3 dedicated decision variables right here. There's a total, and that is the sum of the minimum plus any extra flow. When we set the constraints, we'll go ahead and set that continuity. Okay, I'm going to save some of those. I'm going to go ahead and close a couple of these files. We just don't need anymore. All right, next up is reservoirs. Here we have defined the decision variables to represent the volume of the reservoir at each time step. And then we have state variables to represent the total capacity. So these fields right here for the decision variables, they will be written to the dv.dss file after we run the simulation. And then down here, the capacity values, reservoir 1 is going to have a capacity of 100,000 acre feet. And then reservoirs 2 and 3 will be 120 and 140,000 acre feet total capacity. But keep in mind that all three of these reservoirs are going to start with a starting of 80,000 acre feet of volume. So just keep that in mind. The next file over here is constraints. What we have here is reservoir continuity constraints right here. This basically means that the total inflow to the reservoir, 1 in this case, minus the release equals the change in storage. And then I've done that for all three reservoirs. That's reservoir continuity. Next, we have reservoir capacity. That simply says that the amount of water in the reservoir cannot exceed the total capacity of the reservoir. Those are all hard constraints. Everything here is a hard constraint, it looks like. Then we have continuity at node 4. That means the sum of the 3 inflows equals the outflow. And then continuity within C40, which means the total flow in C40 is the sum of the min plus any extra. And this last one's also important. It's the capacity within this minimum flow constraint. I should actually probably change this to minimum right there. There we go. This is just a comment, but basically means that the minimum flow here cannot exceed the minimum in-stream flow demand. The reason why this is important is because this variable right here, if I go to the next file over, objectives, I'm going to paste in what I have. That's the same variable right here. So the higher this variable, the linear programming algorithm wants to maximize the amount of in-stream flow because it has the highest coefficient that's associated with that flow value in CFS. So these weights that I assigned are fairly arbitrary, 20, 15, and 50, where these 3 decision variables represent the amount of storage in the reservoir. So what we want to do is try to maximize the storage of water in the reservoir, which is not as important as satisfying this downstream flow requirement. Finally, the last file we need to define is right here, main.russell. We have a single sequence. All we're doing basically in this base model is calling our inflows, demands, channels, reservoirs, constraints, and then finally the objective function. Okay, I'm going to go ahead and save all of that. And let's go ahead and go back to the model and see if this runs. Let me refresh real quick. So right click, refresh, boom. Okay, just making sure that we have our files here. I'm going to right click on the launch file now, come down to run as, and then launch. Okay, that looked like it ran. Let's check out to see if we have any results. I like doing that just using DSS view. I'm going to open up the dv.dss file because that's where our decision variables get written to. And boom, here they are. Let's take a look at the reservoir storage in the 3 reservoirs, 1, 2, and 3. After all, this exercise is about balancing the storage between these 3 reservoirs. And here is a table of the data. Keep in mind we have 6 years worth of data, so this is monthly data. First few months we're looking at here is just the starting data. We don't actually start until October of 1921. And then this would be 1 month in, 2 months in, 3 months in, and so on. It looks like Reservoir 1 is taking its priority seriously, which means it's filling up right away and it stays filled. Reservoir 2 is doing the same thing. Reservoir 3 looks like it's fluctuating. Let's go ahead and look at the plot now. Okay, so here is the plot. In green is Reservoir 1. It fills up to its max capacity of 100,000 acre feet. Red represents the volume of water in Reservoir 2. It takes a couple years, but it eventually reaches its max capacity of 120,000 acre feet. And then finally, with the lowest priority and the lowest weight, if you will, in the objective function value is that Reservoir 3 storage that's represented by this yellow line. It finally makes it up to its full capacity of 140,000 acre feet, but it takes basically all 6 years of the simulation to get there. What I want to do in this reservoir system storage balance exercise is to balance out the volume of water in each of these reservoirs over the course of this 6 year simulation. So it looks like we have enough inflow to fill up all three reservoirs to the top by the end of the 6 years. However, how we're doing it seems a little unfair. Reservoir 1 fills up, Reservoir 2 fills up, Reservoir 3 takes forever, but finally fills up. Now in ResSim, we have an implicit system storage balance where all the reservoirs will fill up commensurately based on their volume. And there's also options to sort of customize how you want the reservoirs to be balanced out based on their volume and the total percentage and the total amount of water in the system. I'm going to keep things real simple in this exercise and just do a very equal balance based on volume type of pursuit here, where my goal is for all the reservoirs to have an equal percentage full of the water over the course of the simulation. And keep in mind, we have different demands. We have different inflows for each reservoirs, and the three reservoirs are different sizes, 100,000 acre feet, 120,000 acre feet, and 140,000 acre feet. So to get started with that, I think what may be easiest is to create a decision variable for each of these reservoirs to calculate the percent that that reservoir is full. So at this point right here, we would have 100% reservoir 1, 100% reservoir 2, and then reservoir 3 would be, what is this, 80 out of 140, so that'd be about 57% halfway through 1924. So let's go ahead and get started with that, and then look for strategies on how to equalize the percent full of each of these reservoirs. We go back to my files. I'm going to open up the reservoirs file, and then down below what I have, I'm going to paste in some more code here. So what I've created is three decision variables right here, lines 12 through 14, and this is the percent full of reservoir 1, reservoir 2, and reservoir 3. It's going to write to the DSS file as their own three separate paths with the part C here as percentage. And then down below here, I'm actually creating what is a constraint, but I'm using it to calculate the percent full, which is going to be the storage in the reservoir divided by the capacity. Okay, so I've done that for reservoirs 1, 2, and 3. That looks good. Let's go ahead and run the exact same model just as we saw it before, and then take a look at these calculated percent full for each of the three reservoirs. So I'm going to hit save and then back to Eclipse, right click, come down here to run as, and then launch. Let's go to DSS view and then view, refresh the catalog. Now we have these three new paths for the percent full of reservoir 1, 2, and 3. Let's go ahead and see what that looks like in the table view first. Okay, not surprising, we have 100% in reservoir 1 after just a few months. Reservoir 2 slowly increases until it hits 100%. And then reservoir 3 is just floundering around here, waiting for some more water. Let's take a look at the actual plots though. Okay, this looks similar to what we have before, except now the vertical scale is a percentage from 0 to 1, or rather 0% to 100%. You can see over the course of the 6 water years that eventually all three of the reservoirs are completely filled up to 1 or 100%. It's really not a percentage, it's really a decimal, but whatever, you know what I'm talking about. We're treating this 1.0 as 100%. If I wanted to introduce the actual storage, which would be these values here, so these 6, if I plot it all together, what you see on the top here is the plot we were just looking at. This is the percentage that the reservoir is full, where blue is reservoir 1, red is reservoir 2, and green is reservoir 3. The bottom plot here is the storage of each of the reservoirs as a function of time. This is what we saw earlier, the first time we looked at a plot. Unfortunately, the colors aren't the same because we have reservoir 1 now in green, reservoir 2 in red, I guess that's the same, and then reservoir 3 is in yellow. All right, so the first attempt to keep the reservoirs proportionally equal in terms of their volume, the percent full, you may be tempted to go to the weights, the objective function, and then just set all of these weights equal to the same number. And that is not a good idea, but I'm going to run it anyway, just because you're probably curious what's going to happen. And the fact is, we're going to have a number of non-unique optimal solutions. So I have no idea what's actually going to happen. Ultimately, the reservoirs will fill up, but I'm not really sure how. So just for fun, let's go ahead and run this and launch. Okay, I'm going to bring up DSS view, and then refresh catalog. Let's look at just the percent flow. Actually, let's look at the reservoir volume first. I'm just going to bring up the plots. Okay, this is pretty wild. Definitely different than it was before. Here's reservoir 1. Here's reservoir 2. Here is reservoir 3. So we're definitely not having an equal percentage, but let's take a look at that data anyway. Here's the percentage full for those 3 reservoirs. Let's just take a look at the plots. Reservoir 1, Reservoir 2, and Reservoir 3. What we want is all 3 of these lines to be right on top of each other, regardless of what percentage it is. Okay, so I'm going to close this, minimize that, back to our files. I'm going to set these back to what they were. So what was it? 15 and 10 for 2 and 3, and save. What I'm going to do here is come to the constraints file, and I'm going to add a constraint. It's going to be a soft constraint, but what it's going to do is penalize any deviation in the percent difference, percent volume full difference between all 3 of the reservoirs. So this is what I have to paste in. What we're doing is we're creating a constraint, reservoirs equal full percentage. This is going to specifically address reservoirs 1 and 2. That's why I named it what I did. The left-hand side is the percent full of reservoir 1. The right-hand side is percent full of reservoir 2. And if there's any deviation, what I'm going to do is penalize it by 10. Now, I'm not sure if 10 is enough or not, or maybe too much. Well, let's see what happens. So I'm going to save that. Let's go ahead and run. So right-click, run as, launch. And now to DSS view, refresh catalog. All right, so let's take a look at the percent full for those 3 reservoirs. And it looks like nothing happened. Okay, this is the same results we had originally. We want the red line and the blue line to be on top of each other, which basically tells me we need to increase the penalty. So let's go ahead and give that a shot. Back to this file here. Let's just add a couple zeros. I think that's good enough. We'll see what happens. So right click and run, and let's check out our data. So view, refresh catalog. This is the percent full for all 3 reservoirs, and here is the plot, and cool. Just what we expected to have happen. Reservoir 1 is right here, Reservoir 2 is right here, and then Reservoir 3, which we have not included in this constraint yet, is still doing its thing down here. All right, let's go ahead and plot out the actual volume of water in the 3 reservoirs now. Okay, that looks interesting. Remember, Reservoir 1 is green in this situation, and then Reservoir 2 is red. So they're slowly increasing from, 70% up to about 100% full over the course of a year and a half, maybe 2 years. And then Reservoir 3 is, again, not related to that constraint. That's what we're going to do right now. I'm going to go back to the files. I'm going to just add another constraint right here. This is going to be, we'll just do Reservoir 2 and Reservoir 3 now. That's a 2, that's a 3. We'll leave these very large weights still in place here, and then save. All right, this should be the last time here. Right click and run as 1. Okay. And then view, refresh the catalog. Let's take a look at the percent full for these 3 reservoirs, and boom, very nice. They're all on top of each other. Reservoir 1, Reservoir 2 in red, and then Reservoir 3 in green. Just because I'm curious, I'm gonna look at those results plus the actual volumes in the reservoirs side by side. Here's the plot. And now we see over the course of that 6-year simulation, the percent full starts at around 65%, and then it slowly increases to what is close to 100%. We can actually get the numbers if we go File, Tabulate, and then these 3 columns right here should have pretty much the exact same numbers. All right, well, that was it for this exercise where we created a system with multiple reservoirs and investigated system storage balance so that the percentage of water in each reservoir was equal over the course of this simulation.